The morning of October 7th, 1942, Lieutenant Commander Kijiro Nambu stood in the cavernous interior of the Yokosuka Naval Arsenal, staring at what should have been impossible. Before him, mounted on a steel workbench under the harsh glare of industrial lighting, sat a pristine American M2 Browning heavy machine gun. It had been salvaged 3 weeks earlier from a B-17 Flying Fortress shot down over Luzon, extracted from the burning wreckage before American forces could recover it, created carefully, and shipped across 2,000 miles of ocean to this moment. Nambu reached out and touched the weapon's barrel. The metal was cold, foreign, American. Around him, a dozen engineers and metallurgists from the Imperial Japanese Navy's technical division crowded close, their faces betraying the same mixture of professional curiosity and something deeper hope, perhaps, or hunger. Japan was winning the war in the Pacific, but everyone in that room understood the precarious mathematics of industrial capacity. The Americans built things differently. They built them faster. And this gun, this legendary Mar-Deuce that American bomber crews swore by, represented everything Japan needed to understand about that difference. "Disassemble it completely," Nambu ordered. "I want measurements of every component, photographs from 6 angles, material samples from the barrel, the bolt, the springs, everything." What happened next would take 3 years to fully understand. The measurements would be perfect. The drawings would be flawless. The resulting weapon, designated the Type 5, would look identical to the M2 Browning in every visible dimension. And when Japanese soldiers pulled the trigger in combat, when they needed that gun to keep firing as American forces pressed forward across blood-soaked Pacific beaches, the barrel would begin to glow cherry red after 150 rounds, it would warp after 200, and it would split, catastrophically and fatally, before the crew could fire the 300th round. But that morning, in October 1942, none of that had happened yet. That morning, the captured M2 represented possibility, not failure. It represented the belief that technology could be copied, that American advantages could be neutralized through careful study and Japanese ingenuity. It represented the dangerous assumption that what you can see is all there is to understand. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why the Type 5 program mattered and why its failure would cost lives in ways both immediate and profound, you need to understand the strategic situation Japan faced in late 1942. The 6 months following Pearl Harbor had been a period of almost unbroken Japanese victory. The southern resource area had fallen. The Philippines were conquered. Singapore had surrendered. The speed and scope of Japanese expansion had shocked even Tokyo's most optimistic planners. But beneath the triumph, logistical realities were beginning to assert themselves. Japan's industrial capacity was roughly 1/10 that of the United States. Japanese steel production in 1942 totaled approximately 7 million tons. American steel production that same year exceeded 80 million tons. This disparity cascaded through every aspect of military production: ships, aircraft, vehicles, and, critically, small arms and crew-served weapons. The Imperial Japanese Navy understood this problem with painful clarity. Unlike the Imperial Army, which remained confident in its Type 92 and Type 3 machine guns, the Navy had been studying American weapons development since the 1930s. They knew that the M2 Browning represented a leap forward in heavy machine gun design, not revolutionary, but refined to a degree that Japanese weapons had not yet achieved. The M2 fired a 50 caliber cartridge 12.7 mm in diameter at a cyclic rate of approximately 550 rounds per minute. More importantly, it could sustain that rate of fire for extended periods without overheating or mechanical failure. American bomber crews mounted 4 to 6 M2s on each B-17, and those guns could fire continuously during extended engagements with Japanese fighters. Japanese pilots had learned to respect the M2's range and hitting power. More than one Zero pilot had been killed by 50 caliber rounds fired from a bomber he thought was already crippled. Japan's existing heavy machine guns were not inadequate, precisely, but they were products of an earlier design philosophy. The Type 92, introduced in 1932, was a reliable weapon, but it fired a smaller 7.7mm round and required a crew of 3 to operate effectively. The Type 3, a 13.2mm weapon, had impressive hitting power but was heavy, complex, and prone to stoppages if not meticulously maintained. Neither weapon could match the M2's combination of firepower, reliability, and relative simplicity. The capture of intact M2s in early 1942 offered what appeared to be a shortcut. If Japan could reverse engineer the M2, copy its design exactly, they could field a weapon with proven performance, without the years of development time that American engineers had invested. The Naval General Staff authorized the program in August 1942. The timeline was aggressive, working prototypes by January 1943, production models by summer. Nambu was the logical choice to lead the effort. His uncle, Kijiro Nambu the Elder, had designed the Type 14 pistol, Japan's standard sidearm, and the younger Nambu had inherited both the name and a reputation for careful, methodical engineering. He was 38 years old in 1942, a graduate of the Imperial Japanese Naval Academy's engineering program, and a specialist in small arms design. He had studied American weapons before the war, had examined captured examples from China, and understood or thought he understood the principles that made American firearms effective. The disassembly of the captured M2 began in mid-October and took 3 weeks. The engineers worked with precision instruments, measuring every component to tolerances of 1/100th of a millimeter. They weighed each part. They photographed the weapon from every angle, creating a visual record that filled 2 complete filing cabinets. They test-fired the gun repeatedly, documenting its performance characteristics under various conditions. The barrel received particular attention. It was 45 inches long, with a distinctive perforated jacket that allowed air cooling. The bore showed minimal wear, despite evidence that the gun had seen combat use. When the engineers examined the barrel, under magnification, they found a surface finish that was remarkably consistent, no visible tooling marks, no irregularities that might affect heat distribution or bullet trajectory. They measured the barrel's wall thickness, 0.7 inches at the chamber end, tapering slightly toward the muzzle. They tested its hardness using a Rockwell scale, finding values that indicated a high-strength steel alloy. They took small material samples and conducted spectroscopic analysis, identifying the presence of chromium, molybdenum, and vanadium, in addition to the base iron and carbon. This was where the first invisible problem emerged, though the engineers didn't recognize it yet. The M2's barrel was manufactured from a specific chromium-molybdenum steel alloy designated AISI 4150 by American metallurgical standards. This alloy had been developed over years of testing by American steel companies working in collaboration with military ordnance departments. The exact composition: 0.3% carbon, 0.85% chromium, 0.15% molybdenum, with trace elements of silicon, manganese, and other additives had been refined through thousands of test batches to achieve a specific combination of strength, heat resistance, and machinability. But the composition alone wasn't enough. The heat treatment process was equally critical. After the barrel was machined to its final dimensions, it underwent a carefully controlled heating cycle raised to 1450 degrees Fahrenheit, held at that temperature for precisely 2 hours, then quenched in oil at a specific cooling rate. This was followed by tempering at 600 degrees Fahrenheit for 4 hours, which relieved internal stresses while maintaining hardness. The result was a barrel that could withstand sustained firing temperatures exceeding 1000 degrees Fahrenheit without warping or losing structural integrity. None of this process was visible in the finished barrel. The Japanese engineers could measure the results, the hardness, the dimensions, the weight, but they couldn't observe the thermal history that had created those properties. They knew the approximate alloy composition from their spectroscopic analysis, but not the precise ratios or the importance of trace elements that represented less than 0.01% of the total material. They could see that the barrel had been heat-treated, but not the exact temperature curves or timing that made the treatment effective. They made their best guess. They selected a Japanese naval steel specification, SNB3, which had a similar chromium-molybdenum composition to what they'd measured in the American barrel. Close enough, they concluded. The differences were minor, and Japanese steel quality was excellent. That was something the entire engineering team agreed upon without question. The same pattern repeated throughout the weapon. The M2's recoil spring, for instance, was manufactured from silicon chromium steel wire, heat-treated to achieve a specific elastic modulus. The Japanese engineers could measure the spring's force curve, how much it compressed under various loads, but they couldn't determine the number of thermal cycles or the precise carbon content that gave it durability through tens of thousands of compression cycles. They specified a Japanese spring steel, SKS5, that had similar initial properties. The bolt assembly presented another challenge. The M2's bolt locked into the barrel extension using rotating lugs, a proven mechanism, simple and effective. But the locking surface finish was critical. Too rough, and the lugs would wear quickly, leading to headspace problems and eventual catastrophic failure. Too smooth, and the lugs might slip under the high pressures generated by firing. American manufacturers achieved the correct finish through a combination of precision machining and a final honing process that the Japanese engineers could observe but not fully quantify. They replicated what they could see. They machined the bolt lugs to match the American dimensions exactly. They achieved a surface finish that looked identical under visual inspection. But surface finish isn't just about appearance, it's about the microscopic geometry of metal crystals, the distribution of residual stresses, the work hardening that occurs during machining. These factors affect friction, wear resistance, and heat dissipation in ways that aren't immediately apparent. By late December 1942, Nambu's team had completed detailed engineering drawings for every component of the Type 5. On paper, the weapon was a precise copy of the M2 Browning. The dimensions matched within machining tolerances. The weight was within 2% of the original. The operating mechanism was functionally identical. The drawings went to the Yokosuka Arsenal's machine shops in early January 1943. Skilled, Japanese craftsmen began manufacturing the first prototype components. These were not assembly line workers, they were tool makers and precision machinists, men who had apprenticed for years to learn their trade. They took pride in their work and understood the importance of the project. If Japan could field a weapon equivalent to the M2, it would narrow, if only slightly, the industrial gap with America. The first complete Type 5 prototype was assembled in late February 1943. Visually, it was indistinguishable from the American original. The weight balance felt correct. The mechanism operated smoothly when hand-cycled. Everything suggested success. On March 3, 1943, the prototype was taken to the Yokosuka Naval Arsenal's weapons testing range for its first live-fire trial. The range was located on the arsenal's eastern edge, facing Tokyo Bay. It consisted of a series of reinforced concrete bunkers with firing points overlooking a bullet trap, backed by earthen berms. The day was cold and overcast, typical for early March in the Kanto region. The test protocol was straightforward. Fire 250 rounds in sustained bursts, measuring cyclic rate, accuracy, and barrel temperature at regular intervals. 250 rounds represented a reasonable combat load, enough to engage multiple targets or sustain fire during a prolonged defensive action. The American M2 could fire this quantity without difficulty, often without even requiring a barrel change. Nambu watched from the observation bunker as the gun crew, 3 experienced naval ratings who had trained on captured American weapons loaded the first belt of ammunition. The ammunition itself was Japanese-manufactured 12.7mm rounds, copied from American .50 caliber specifications. The cartridge cases were slightly different in composition from American brass, but the dimensions and ballistic properties were nearly identical. The first burst was 50 rounds, fired over approximately 6 seconds. The sound was sharp and distinctive, the heavy mechanical clatter of the action cycling, punctuated by the bass thump of each round leaving the barrel. Downrange, target boards splintered and disintegrated. The cyclic rate was correct, approximately 550 rounds per minute. Accuracy appeared good, with rounds grouping within expected parameters at 300 meters. The gun crew paused, checking for any immediate malfunctions. Finding none, they prepared for the second burst. 75 rounds into the test, Nambu noticed something. The barrel, visible through binoculars from the observation bunker, was beginning to show a faint discoloration, a heat shimmer in the air around the metal. This was normal to some degree, but it seemed more pronounced than expected. He made a note on his observation sheet. Barrel heating, round 75. At 100 rounds, the barrel was visibly glowing in the dim morning light, not dramatically, but enough to be seen without magnification. The gun crew exchanged glances. One of them, a petty officer who had operated a captured M2 during training exercises, looked concerned. The American gun hadn't glowed brightly this quickly. At 130 rounds, the rate of fire began to slow. Not much, perhaps 50 rounds per minute less than the initial cyclic rate, but measurable. The gun crew reported this immediately. Nambu ordered them to continue firing. At 160 rounds, the barrel was cherry red. Even from the observation bunker, 60 meters away, Nambu could feel the heat radiating from the weapon. The cyclic rate had dropped to approximately 450 rounds per minute. More concerning, the weapons report had changed. There was a slight irregularity in the timing of shots, suggesting that the action was binding or that gas pressure was fluctuating. At 185 rounds, the feed mechanism jammed. The gun crew immediately implemented clearance procedures, but when they opened the receiver, they discovered that a round had failed to chamber fully. The bolt was stuck partially forward, unable to complete its cycle. Worse, the barrel was now glowing bright orange, far too hot to touch, even with insulated gloves. They waited 15 minutes for the barrel to cool enough to safely investigate the malfunction. When they finally extracted the jammed round, they discovered that the case had expanded slightly, not enough to rupture, but enough to prevent smooth feeding. This shouldn't have happened. American .50 caliber brass was designed to withstand chamber pressures in excess of 50,000 psi without significant deformation. After the barrel cooled sufficiently, they resumed firing. But at round 198, the weapon jammed again, different symptom, same underlying cause. The action was running too hot, causing thermal expansion that threw off the carefully calibrated tolerances between moving parts. At round 203, disaster. A burst of 5 rounds, then a sound that every weapons engineer dreads, a sharp metallic crack, followed by an immediate cessation of fire. The barrel had split longitudinally along a 6-inch section, approximately 18 inches from the chamber. Not catastrophically, no explosion, no injury to the crew, but definitively. The weapon was inoperable. Nambu stood in silence for a long moment, staring at the failed barrel through his binoculars. Around him, the other engineers began speaking quietly among themselves, hypotheses, suggestions, attempts to explain what had happened. He ignored them. He was calculating the implications. 203 rounds. The American M2 could fire 5 times that number without requiring a barrel change. Some bomber crews reported firing over 2,000 rounds in a single mission without mechanical failure. The Type 5, supposedly an exact copy, had lasted barely 10% of that duration. The barrel was transported back to the metallurgy laboratory for analysis. Under microscopic examination, the failure became clearer. The split had initiated at a point where the barrel's internal structure showed signs of thermal stress, microscopic cracks that had propagated rapidly once the metal reached a critical temperature. The heat treatment hadn't been adequate. The steel itself, while good quality by Japanese standards, lacked something that the American alloy possessed. Exactly what that something was remains unclear. Over the following months, Nambu's team tried 17 different variations. They modified the steel composition, adding more chromium in some iterations, more molybdenum in others. They experimented with different heat treatment schedules, higher temperatures, longer soak times, slower cooling rates. They tried thicker barrel walls, which added weight but theoretically improved heat dissipation. They tried thinner walls with enhanced air cooling, which reduced weight but made the barrel more susceptible to warping. Each iteration was an improvement over the last. By July 1943, they had achieved a design that could fire approximately 350 rounds before catastrophic failure, nearly double the initial prototype's performance. Still inadequate by M2 standards, but closer. The question facing the Naval General Staff was whether closer was close enough. The war was not waiting for perfection. By mid-1943, the strategic picture was darkening. Guadalcanal had been lost. The Solomon Islands were under pressure. American industrial production was accelerating. Intelligence reports indicated that American factories were now producing more aircraft per month than Japan could produce in a year. The gap was widening, not narrowing. There were advocates within the Naval General Staff who argued for accepting the Type 5's limitations and beginning production anyway. A gun that could fire 350 rounds before failure was still better than Japan's existing heavy machine guns in terms of hitting power and range. In defensive positions, where the gun could be emplaced with spare barrels and adequate cooling time between engagements, the limitations might be manageable. Nambu opposed this position. He understood what would happen if they fielded a weapon that failed predictably in sustained combat. Machine gun crews developed tactics and timing based on their weapon's reliability. If you knew your gun could keep firing as long as you had ammunition, you fought differently than if you knew it would fail after a few minutes of sustained fire. The psychological impact of weapon failure in combat, watching your gun split its barrel while enemy forces advanced, would be devastating to unit cohesion and morale. But Nambu was an engineer, not an admiral. The decision was made above his level. In August 1943, a limited production run of Type 5 machine guns was authorized, approximately 200 weapons, to be issued to naval landing forces for field evaluation. The official designation was operational testing. In practice, it meant combat. The island of New Georgia sits in the central Solomon Islands, roughly 200 miles northwest of Guadalcanal. In June 1943, it represented the next logical step in the American advance toward Rabaul, the massive Japanese base that anchored their defensive perimeter in the South Pacific. New Georgia possessed an airfield at Munda Point, and whoever controlled that airfield controlled the air approaches to the Upper Solomons. The Japanese garrison on New Georgia numbered approximately 10,000 men, a mix of Imperial Army and Special Naval Landing Force personnel. They had been fortifying the island since March, constructing an elaborate network of bunkers, pillboxes, and interconnected defensive positions. The terrain favored defense-dense, jungle, steep ridges, limited beaches suitable for amphibious assault. Japanese commanders were confident they could hold the island for months, possibly longer. Among the weapons delivered to New Georgia in early June 1943 were 23 Type 5 heavy machine guns. They were issued to Special Naval Landing Force units, assigned to beach defense, the positions most likely to face sustained combat during the expected American invasion. Each gun came with a basic load of 1,000 rounds of 12.7mm ammunition, spare barrels, and detailed technical manuals that emphasized the importance of barrel cooling and burst discipline. The gun crews received 2 weeks of training on the new weapons. Most were experienced machine gunners who had previously operated Type 92 seconds or captured weapons. They found the Type 5. Familiar, the operating mechanism was similar to other recoil-operated machine guns they had used. The weapon felt well balanced, and its hitting power during training exercises was impressive. Several crews reported that they preferred it to their old Type 92 seconds, despite its greater weight. What they weren't told, what their commanders may not have fully understood, was that the Type 5 had never been tested in genuine combat conditions. The weapons had been evaluated on test ranges, where firing was controlled and methodical, where cooling periods were observed, where the psychological pressure of incoming fire didn't exist. Combat was different. In combat, you didn't fire measured bursts with rest periods. In combat, you fired until the threat was eliminated or until you were dead. The American invasion of New Georgia began on July 2nd, 1943. The initial landings were conducted by elements of the USA. Army's 43rd Infantry Division and Marine Corps raiders, supported by naval gunfire and airstrikes. The Japanese defensive plan called for allowing the Americans to land, then engaging them from prepared positions as they advanced inland. Machine gun fire would be the anchor of this defense, breaking up American formations and inflicting casualties that would slow the advance to a crawl. For the first 2 days, the plan worked reasonably well. American forces established beachheads, but faced fierce resistance when they pushed beyond the coastal areas. Japanese machine gun positions covered every likely avenue of approach, and American casualties began to mount. Among the defenders, the Type 5 crews reported excellent results. The weapons' range and accuracy exceeded expectations, and its psychological effect on American infantry was notable. Soldiers who had faced 7.7mm fire before found the heavier 12.7mm rounds distinctly more intimidating. But on July 4th, during an intense firefight near Zanana Beach, the first Type 5 failure occurred in combat. The position was a reinforced bunker overlooking a jungle trail that American forces were using to move supplies forward. A 3-man crew, Petty Officer First Class Hiroshi Tanaka, Seaman First Class Kenji Yoshida, and Seaman Second Class Takeshi Nakamura, had been engaging American troops intermittently since dawn. By early afternoon, they had fired approximately 130 rounds in short bursts, following their training protocols. The barrel was hot but manageable. Discipline had been maintained. Then, an American platoon, roughly 30 men, emerged from the jungle trail, approximately 200 meters from the bunker. They were moving in column formation, exposed, perfect targets. Tanaka opened fire immediately. The first burst, 15 rounds, cut down 3 Americans and sent the rest diving for cover. The second burst, 20 rounds, suppressed return fire and hit at least 1 more soldier. The Americans began attempting to flank the position, moving through the jungle on both sides of the trail. Tanaka continued firing, longer bursts, now, trying to keep multiple groups of Americans pinned down simultaneously. 50 rounds, 75, 100. The barrel began to glow visibly even in the bright afternoon sunlight. Yoshida, the assistant gunner, glanced nervously at it but said nothing. They were in combat. The Americans were still coming. At approximately 160 rounds, the cyclic rate began to drop. Tanaka noticed it immediately. The rhythm of the gun changed, becoming irregular. At 180 rounds, the feed mechanism jammed. Yoshida cleared it quickly, but the barrel was now cherry red, radiating heat that made the air shimmer. At 195 rounds, another jam. This time, when Yoshida opened the receiver, he found that the bolt was stuck partially forward. The metal had expanded from heat, throwing off the tolerances that allowed smooth operation. They waited. 30 seconds. A minute. The Americans were using the lull to advance, working their way closer through the jungle. Yoshida finally got the bolt free, and Tanaka resumed firing. 8 rounds, 12 rounds. Then a sound that Tanaka would describe later. in a diary entry written 3 days before he was killed, as, like a bamboo stick breaking. The barrel split. Not explosively, no shrapnel, no immediate danger to the crew, but definitively. A 6-inch longitudinal crack appeared approximately 2 feet from the chamber, and the weapon ceased firing. 203 rounds. Exactly the same failure mode that had occurred during testing at Yokosuka, now repeated in combat with American infantry advancing on 3 sides. Tanaka made the only decision available to him. They abandoned the position, carrying their rifles and as much ammunition as they could manage, leaving the Type 5 behind. The Americans overran the bunker 20 minutes later. The machine gun, still hot enough to burn skin, sat silent with its split barrel and approximately 750 rounds of unfired ammunition stacked beside it. This pattern repeated across New Georgia over the following week. Not every Type 5 failed, some positions were overrun before the guns reached their failure threshold, and some crews were killed by American fire before their weapons gave out. But enough failed, and failed consistently, that reports began filtering back to Japanese commanders. Machine gun positions that should have been able to sustain defensive fire for hours were falling silent after 10 or 15 minutes of sustained combat. A Marine sergeant named Robert Fletcher, serving with the 1st Marine Raider Battalion, noted the phenomenon in a letter home dated July 10, 1943. "We've been hitting these Jap positions all week, and something strange is happening. Their machine guns will be firing like crazy, really pouring it on, and then they just stop. Not because we got them, the position is still intact, and we can see the gun is still there. They just stop firing and pull back. We thought maybe they were trying to draw us in, but when we finally took the position, the gun was just sitting there with plenty of ammunition. The barrel looks like someone took a welding torch to it. Bent all to hell. I don't know what they're doing wrong, but I'm not complaining." The psychological impact on Japanese crews was severe. The tactical doctrine drilled into every machine gunner emphasized the weapon as the foundation of defensive positions. Riflemen relied on machine gun support to break up enemy assaults and provide covering fire. When that support failed, not because of enemy action, but because the weapon itself betrayed you, it created a crisis of confidence that extended beyond the immediate crew. Seaman First Class Saburo Kawamoto, a member of a Type 5 crew positioned near Munda Point, kept a diary that was recovered after his death in late July. The entry dated July 12 reads, "Corporal Ishida's gun failed this morning during the American attack. The barrel split after perhaps 10 minutes of firing. We could hear it happen, the change in sound, then silence. Ishida was screaming for us to provide covering fire, but our position was too far to help. The Americans overran his bunker. 3 men died because the gun stopped working. Tonight, Petty Officer Yamada told us to be careful with our Type 5, to fire in short bursts only. But if we do that, how can we stop the Americans when they attack in force? What is the point of a machine gun that cannot sustain fire?" By late July, Japanese commanders on New Georgia had effectively lost confidence in the Type 5. Orders were issued to replace them with Type 92 seconds wherever possible, despite the Type 92's inferior range and hitting power. The remaining Type 5 seconds were relegated to secondary positions or used in situations where sustained fire was unlikely to be necessary. Some were simply abandoned as units withdrew to new defensive lines. The American after-action reports from New Georgia documented 17 separate instances of captured Japanese positions where Type 5 machine guns were found intact with substantial ammunition remaining. In each case, the barrel showed signs of extreme heat damage, warping, discoloration, or longitudinal cracking. Intelligence officers noted the pattern and forwarded reports to higher headquarters, but the strategic significance was unclear. The Type 5 was an unknown weapon, and American analysts initially assumed they were looking at isolated manufacturing defects rather than a systemic failure. The New Georgia campaign officially ended on August 5, 1943, with American forces in control of the island and the Munda airfield. Japanese casualties exceeded 7,000 killed, wounded, or missing. Among the dead was Petty Officer First Class Hiroshi Tanaka, killed by artillery fire on July 18th while attempting to hold a defensive position with a Type 92 machine gun after his Type 5 had been evacuated to the rear due to barrel failure. The reports from New Georgia reached the Naval General Staff in Tokyo by mid-August. The language in the official summaries was carefully diplomatic: operational limitations in sustained fire scenarios, recommended modifications to cooling procedures, temporary suspension of field, and deployment pending technical review. But the underlying message was clear: the Type 5 program had failed. The weapon could not perform the fundamental mission of a heavy machine gun, which was to provide sustained suppressive fire under combat conditions. Nambu received the reports in late August 1943. He read them in his office at the Yokosuka arsenal, alone, late in the evening. The technical details matched exactly what he had observed during the original test firing in March: barrel overheating, feed mechanism jams, catastrophic failure at approximately 200 rounds. Except now, instead of a controlled test on a firing range, these failures had occurred with American infantry advancing and Japanese soldiers dying. He wrote in his personal notes, discovered after the war, "We measured everything that could be measured. We replicated every visible dimension. We matched the weight, the mechanism, the external appearance. But we could not replicate what we could not see: the accumulated knowledge embedded in American manufacturing processes, the quality control standards, the metallurgical expertise developed over decades. We built a weapon that looked like an M2 Browning. We did not build an M2 Browning. 23 guns were sent to New Georgia. I do not know how many men died because those guns failed. I will never know. That is perhaps appropriate." The Type 5 program was officially terminated in September 1943. The remaining production weapons, approximately 170 units that had not been shipped to combat zones, were evaluated for alternative uses. Some were converted to training weapons, their limitations considered acceptable in non-combat scenarios. Others were simply placed in storage. A few were shipped to secondary defensive positions where sustained fire was deemed unlikely. None were issued to frontline combat units again. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical autopsy of the Type 5 program, conducted by the Naval Technical Research Institute in late 1943, identified the core problems with painful precision. The barrel metallurgy was inadequate, the Japanese steel alloy, while similar in composition to the American chrome moly specification, lacked the exact trace elements and heat treatment protocols that gave the M2 barrel its heat resistance. The difference amounted to less than 1% of the total material composition, but that 1% determined whether the barrel could withstand sustained fire or fail catastrophically. The bolt assembly had similar issues. The surface finish that the Japanese engineers had replicated visually was not, it turned out, the actual critical factor. What mattered was the subsurface microstructure, the alignment of metal crystals, the distribution of carbides, the work-hardening profile that affected wear resistance. These properties were determined by manufacturing processes that left no visible trace in the finished component. Even the ammunition contributed to the problem. Japanese 12.7mm rounds, while dimensionally identical to American .50 caliber cartridges, used slightly different powder formulations and primer compounds. These differences affected chamber pressure curves in subtle ways. Peak pressures that were fractionally higher or that occurred fractionally earlier in the firing cycle. Over hundreds of rounds, these tiny variations accumulated, adding thermal stress to a barrel that was already operating at its thermal limits. The Americans, when they eventually captured and tested Type 5 specimens after the war, were professionally curious about the failure modes. A U.S. Army Technical Intelligence Report dated March 1946 noted, The Type 5 represents a competent attempt to reverse engineer the M2 Browning. The dimensional accuracy is impressive, and the basic mechanical function is sound. The failure appears to stem from metallurgical limitations and insufficient understanding of thermal management in sustained fire applications. Japanese steel quality was generally good, but the specific alloy compositions and heat treatment protocols required for this application were beyond their industrial capacity to replicate reliably. The report was technically accurate but understated the human cost. The Type 5's failure wasn't just a matter of metallurgy and thermal management. It was about the gap between what could be measured and what had to be understood. It was about the difference between copying a design and replicating the industrial ecosystem that made that design possible. And it was about the young men who pulled triggers on weapons they believed would keep firing, only to watch barrels split and mechanisms seize while enemy soldiers advanced. After New Georgia, the Type 5 became a footnote in Japanese weapons development, a failed experiment that consumed resources and produced no tactical advantage. But the lessons of the program, or rather the failure to fully internalize those lessons, would echo through other Japanese reverse engineering efforts for the remainder of the war. In late 1943, Japanese engineers attempted to copy the American Norden bombsight, captured from a downed B-24 over truck. The resulting device, designated the Type 1 automatic bombsight, looked superficially similar, but lacked the precision gyroscopes and mechanical computing mechanisms that made the Norden effective. It was fielded in limited numbers, but proved unreliable, and Japanese bombardiers eventually reverted to manual bombing techniques. In 1944, the Imperial Army captured an American M4 Sherman tank in the Philippines and attempted to reverse engineer its suspension system and gun stabilization. The project was abandoned after 6 months, when it became clear that Japan lacked the manufacturing capacity to produce the required components in meaningful quantities. The Americans were building Shermans at a rate of over 1,000 per month. Japan couldn't match that production even if they had successfully copied the design. The pattern was consistent. Japanese engineers could replicate what they could see, but they couldn't replicate the invisible infrastructure, the specialized machine tools, the quality control systems, the supply chains, the institutional knowledge that made American weapons effective at scale. This wasn't a failure of Japanese technical competence. The engineers and scientists working on these programs were highly skilled professionals who understood the theoretical principles involved. The problem was systemic. American weapons development in World War II was the product of an industrial ecosystem that had been evolving for decades. Standardized manufacturing processes, vast research and development budgets, close collaboration between military ordnance departments and private industry, and above all, an economy that could dedicate enormous resources to weapons production without compromising civilian needs. Japan, by contrast, was operating with a fraction of that industrial capacity and was already stretched to its limits, maintaining existing weapons production. The steel that went into failed Type 5 barrels was steel that couldn't be used for ship construction or aircraft production. The machine shop hours spent manufacturing Type 5 components were hours that couldn't be spent on other weapons. Every failed reverse engineering project represented an opportunity cost that Japan, with its limited resources, could not afford. Lieutenant Commander Nambu remained at the Yokosuka Naval Arsenal until the end of the war, working on various small arms projects, but never again leading a major weapons development program. Colleagues who worked with him in the final years of the war described him as meticulous but cautious, reluctant to make optimistic promises about development timelines or performance specifications. The Type 5 experience had taught him something about the limits of reverse engineering, but it had also taught him something darker about the cost of failure in wartime. After Japan's surrender in August 1945, American technical intelligence teams descended on Japanese military installations to catalogue and evaluate weapons development programs. The Type 5 was among the weapons examined, and several specimens were shipped back to Aberdeen Proving Ground in Maryland for detailed testing. The American evaluations were thorough and, in their own way, respectful. The engineers who examined the Type 5 recognized the skill that had gone into its manufacture. The machining quality was high, the attention to detail evident, but the fundamental limitations were equally obvious. A test firing conducted at Aberdeen in December 1945 produced results nearly identical to the original Japanese trials: barrel failure at approximately 200 rounds, feed mechanism jams due to thermal expansion, catastrophic structural failure before the 300th round. The technical report concluded with a paragraph that, in its clinical language, captured the essential tragedy of the Type 5 program. The Type 5 heavy machine gun represents a competent attempt to replicate the M2 Browning through reverse engineering. The dimensional accuracy and mechanical function demonstrate significant technical skill. However, the weapon's inability to sustain fire beyond approximately 200 rounds renders it unsuitable for its intended role. This limitation appears to stem from material science constraints rather than design flaws. The Japanese industrial base, while capable of producing high-quality steel, lacked access to the specific alloy compositions and heat treatment protocols required for this application. The result is a weapon that superficially resembles the M2 but cannot replicate its operational performance. Nambu himself never spoke publicly about the Type 5 program. After the war, he returned to civilian life, working as a consulting engineer for several Japanese manufacturing firms during the Reconstruction period. Former colleagues who maintained contact with him reported that he was reluctant to discuss his wartime work, deflecting questions with vague references to technical challenges and resource limitations. But in private notes discovered after his death in 1978, Nambu wrote more candidly about the experience. One passage, dated December 1952, reads, "We believed that if we could measure something precisely enough, we could replicate it. We measured the M2 Browning down to fractions of a millimeter. We photographed every component, we analyzed the materials, and we built a weapon that looked identical. But we could not build the decades of American industrial experience that went into developing those materials. We could not build the supply chains that ensured consistent quality across millions of parts. We could not build the institutional knowledge that American engineers had accumulated through years of trial and error. We built a copy of a machine. We did not build the system that made that machine possible. And men died because we did not understand the difference." The broader strategic implications of the Type 5 failure extended beyond the weapon itself. The program represented a fundamental misunderstanding of the nature of technological advantage in modern industrial warfare. Japan entered World War II, believing that tactical skill, fighting spirit, and initial technological parity in certain areas, particularly naval aviation and torpedo technology, could offset America's industrial superiority. The Type 5 program demonstrated that technological parity was an illusion. America's advantage wasn't just that they built good weapons. It was that they could build those weapons in vast quantities while continuously improving them, all supported by an industrial infrastructure that Japan couldn't match or replicate. By 1944, this reality had become impossible to ignore. American bomber production exceeded Japanese production by a factor of 10 to 1. American shipyards were launching aircraft carriers faster than Japan could train pilots to fly from them. The M2, Browning the weapon Japan had tried and failed to copy, was being produced at a rate of over 50,000 units per year, mounted on everything from jeeps to bombers to naval vessels. The soldiers and sailors who fought with Type 5 seconds on New Georgia and elsewhere didn't understand these strategic realities. They understood only that their weapon had failed when they needed it most. Some blamed themselves, wondering if they had violated training protocols or failed to maintain the weapon properly. Others blamed their commanders, suspecting that they had been issued defective equipment. Very few understood that they had been given a weapon that was fundamentally incapable of performing its mission, not because of any individual failure, but because the industrial gap between Japan and America was too wide to bridge through reverse engineering alone. The survivors of New Georgia who had operated Type 5 seconds, and there were not many, the casualty rate among machine gun crews was severe, carried memories of those failures for the rest of their lives. In post-war interviews conducted by Japanese historians in the 1960s and 70s, several veterans mentioned the Type 5 specifically. 1. A former Seaman First Class named Koji Matsuda described it this way: "We were told it was as good as the American gun. We believed that. It looked right. It felt right. And when we test-fired it before the invasion, it worked fine. But in combat, when you really needed it to keep firing, it stopped. The barrel would start to glow, and you knew what was coming. You could feel it in the rhythm of the gun, the way it started to slow down, the way the sound changed. And then it would jam, or the barrel would crack, and suddenly you had nothing. The Americans would keep coming, and you had nothing. That was the worst feeling, not being afraid of the enemy, but not trusting your own weapon." The technical lessons of the Type 5 were not entirely wasted. Post-war Japanese industry, rebuilding from the ashes of defeat, took a different approach to technology acquisition. Rather than attempting to copy American or European products through reverse engineering, Japanese companies in the 1950s and 60s licensed technologies, formed partnerships, and invested heavily in understanding the fundamental principles rather than just replicating visible results. This approach, learning rather than copying, proved far more successful and contributed to Japan's emergence as a technological and industrial power by the 1970s. But that was a different era, a different context. In 1942, when Nambu first examined the captured M2 Browning, the pressure to find quick solutions was overwhelming. The war was not waiting for Japan to develop its own advanced weapons from first principles. The gap needed to be closed immediately, and reverse engineering seemed like the fastest path. It wasn't, but by the time that became clear, the price had already been paid. The M2 Browning, meanwhile, continued its service long after World War II ended. The same basic design, refined and improved but fundamentally unchanged, served through the Korean War, Vietnam, Desert Storm, Iraq, Afghanistan, and into the 21st century. As of 2025, the M2 remains in service with the US military and numerous allied nations, more than 100 years after John Moses Browning first designed it. This longevity is not accidental. It reflects the depth of engineering knowledge, the quality of manufacturing, and the continuous refinement that went into the weapons development, exactly the factors that Japan couldn't replicate through reverse engineering alone. There's a broader lesson here that extends beyond weapons and war. In any field, technology, manufacturing, science, the visible product is only the tip of the iceberg. Beneath the surface lies an entire ecosystem of knowledge, experience, processes, and infrastructure that makes that product possible. You can copy what you can see. You cannot copy what you cannot observe. And the gap between those two things, between superficial replication and true understanding, can be measured in performance, reliability, and in the case of the Type 5, in lives. When Lieutenant Commander Nambu stood in the Yokosuka Arsenal in October 1942, examining the captured M2 Browning, he was looking at a machine gun. What he couldn't see was the entire American industrial complex that had produced it, the steel mills, the heat treatment facilities, the precision machine tools, the quality control systems, the testing protocols, the accumulated knowledge of thousands of engineers and metallurgists. He couldn't see any of that, and so he couldn't copy it. The Type 5 looked like an M2 Browning. It had the same dimensions, the same weight, the same basic mechanism. It even sounded like an M2 when it fired. For approximately 150 rounds, it performed identically, and then the barrel began to glow, and then it warped, and then it split, and the illusion died. In war, as in engineering, illusions are luxuries no one can afford. The visible is seductive. It suggests that understanding is simple, that replication is straightforward, that gaps can be closed through measurement and careful copying. But the invisible is what matters. The invisible is where true capability resides. The invisible is what determines whether a weapon fires its 300th round or fails at 203. Japan learned this lesson at terrible cost. The Type 5 program consumed resources Japan could not spare, produced a weapon that could not perform, and contributed to casualties that could not be recovered. It was a failure born not of incompetence but of misunderstanding, a belief that the visible was all there was to see. The barrels that melted after 200 rounds were teaching a lesson that Japan, in 1942, was not yet ready to learn, that in modern industrial warfare, technological superiority cannot be copied. It must be built, slowly and systematically, on foundations of industrial capacity, scientific knowledge, and accumulated experience. There are no shortcuts. There is no reverse engineering your way to parity when the gap is measured not in designs but in entire industrial ecosystems. 23 Type 5 machine guns went to New Georgia in June 1943. By August, most were abandoned or destroyed. The men who operated them learned, in the most brutal classroom imaginable, that a weapon that looks like the real thing is not the same as a weapon that is the real thing. That distinction, measured in fractions of a % of alloy composition and degrees of heat treatment temperature, cost lives. How many lives, precisely, will never be known. But each one represents the gap between what could be seen and what needed to be understood. Each one represents the cost of believing that copying is the same as knowing. Each one represents the price of an illusion that lasted, under sustained fire, approximately 200 rounds. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.